So welcome to lecture 10 of MCS 471 on numerical analysis, or more specifically on numerical linear algebra. This is our third lecture on numerical linear algebra. In lecture 8, we started with the matrix vector notation, and we defined the LU factorization. In the last lecture, in lecture 9, we defined vector norms, matrix norms, and numerical conditioning. So today we will define a better way to do the row reduction, a better way to do the LU factorization. Actually, we will define the PLU factorization, introducing partial pivoting. So this will lead to the definition of numerical stability. As we will see in the first part of this lecture, the algorithm that we covered in lecture 8 is actually an example of a numerically unstable algorithm. So there are two parts in this lecture. We first motivate why the algorithm that we've covered in lecture 8 is actually not a good algorithm. And then in the second part of this lecture, we show a numerically stable LU factorization. So why do we need pivoting? Well, here is a very simple example. And this example also serves somehow as a reminder of the matrix notation. So we start with a system of two equations where the coefficients in the matrix are actually all at random, except the very first one. We have this tiny little epsilon sitting there. So epsilon is not 0. So it's a very small number, not 0. The right-hand side vector is not b1, b2, but actually we picked it such that we know the exact solution. So actually we did the evaluation of the left-hand side at the 1, 1. So mathematically this is a perfectly nice problem. So we said that we had a unique solution if the determinant is different from 0. And that's the case here. So the coefficients in the matrix, except epsilon, are all actually random numbers. And there's no reason why these numbers should be 0. So in lecture 8, we introduced the matrix notation of the row reduction operation. So what we do is we want to make the matrix A, we want to reduce the matrix A to an upper triangular matrix, and we can do this by subtracting from the second row the first row multiplied with the second element, the element that we want to reduce to 0, but then divided by the first element in that column. So you can verify, so this is a perfectly valid operation. Epsilon is not 0. So we can do this. And that is actually the very simplest instance of our LU factorization. So we reduce A to an upper triangular matrix. And then we see that the operation, the row reduction, can actually be written as a multiplication, as a matrix-matrix multiplication. So the operation, the row reduction operation here, is actually defining the L in the LU factorization. So the L times the U actually gives us back the matrix. And you can easily verify this. So the L is actually, you can see this as adding to the second row a multiple of the first row again. So actually changing things again, so undoing things. All right, so why everything is going fine. So let's continue. So in lecture 8, we also covered forward and backward substitution. So we want to solve matrix. So the reduction of the linear system has now led to an upper triangular linear system. But we first have to solve a lower triangular linear system. So the lower triangular system has the given right-hand side B, so the B is now this again, so not B1, B2, and the solution that we find from the forward substitution is then actually used in the right-hand side vector. So we motivated this, we justified this way of working in lecture 8. Now we can do this here all symbolically, and everything goes well, although we already observe some very huge numbers. That is where things are starting to look a little bit suspicious. So we need 1, 1, and we kind of have very huge numbers as intermediate results. Now, if we then do the back substitution, so what we actually find is that suppose now if the epsilon would be so tiny so that adding 1 would still be 1 over epsilon. So that's a kind of a reverse implication from the machine precision. Remember, we defined machine precision as the smallest number you can add to 1 and still make a difference. But if you take 1 over that machine precision, then adding that will give you a very large number, and adding 1 to it will actually also not make a difference anymore. And that is actually happening here. If you take epsilon really tiny, smaller than machine precision, then actually you find that the first x1 is actually 0. And that's very far from 1. So we have lost all our precision. So the working precision, if we worked with 16 decimal places on this very tiny problem, we have no accuracy in the solution. So that is a catastrophic calculation. Now we can easily fix this if we swap the rows. So here we're swapping the rows with a matrix notation. So swapping the rows can be expressed as a matrix multiplication. So here it is explicitly calculated. You can again verify this very easily. Permutation matrices are their own inverse, so swapping again gives you the original. And then you see that actually we also have to do the swap on the right hand side. So our original system is still the LU factorization, so reduced to 2 upper triangular systems, but the right hand side is actually what we call permuted. So if we then do the row reduction, then actually we subtract a very tiny number. So the epsilon now appears in the numerator, no longer in the denominator. We subtract with a tiny number. So actually we had a tiny number that we had to reduce to 0, so we subtract a tiny number. And then actually, if we continue with the forward and the backward substitution, then actually as this epsilon gets very tiny, we can ignore the terms also, but then actually nothing bad happens. So we see that if the epsilon would be the machine precision or less, then actually it would not make any difference. So the x1 and the x2 are actually 1 plus the order of that epsilon, if we actually ignore the terms here. Of course, for larger epsilons, if the epsilon is 1, for example, then you just calculate with all the numbers here. All right, so we have seen two ways now to solve this linear system, this 2 by 2 system. The first with the algorithm that we have covered in lecture 8 with the LU factorization. So that actually turns now out to be a very bad way to solve linear systems, but we have a better way. And the main part of this lecture will actually be to uh, express that better way, that row pivoting way, in a more general fashion. So we will derive a new algorithm. All right, our first exercise is actually now a numerical example. So if you did not really like the symbolic notations, well, let's redo everything with numbers. Um, So what this exercise actually asks you to do is to redo everything that was already there, but now with the epsilon equal to 10 to the power minus 8. And what you should observe is that with the LU factorization of lecture 8, so you can use a Julia session, so you can actually do this with the lufac program, with the lufac function that was posted in lecture 8. So you will then actually see that the errors are actually quite large. Now, in the last lecture, we also had very large errors, but that was because we worked with matrices that were bad. So this matrix actually has a very nice condition number. So there's actually nothing wrong with this matrix. So you can also, that's additional uh, calculation, would be simply to compute a condition number, that as we have seen in lecture 9. Okay, 2 by 2 matrix. So let's do this a little bit more systematic. So the second exercise asks you to build matrices that have smaller and smaller elements on the diagonal. So this is an experiment where you take a random matrix and you replace the diagonal with a number that is 10 to the power minus k, where k starts actually quite large, but then actually it gets to 10 to the power minus 10. So in Julia, I give the instructions here. So you have this matrix R, and you generate a vector, you make a vector of ones to give you the right-hand side. So we know what the exact solution is. And then you run the lufac function of lecture 8, followed by the forward and the back substitution. So you could have used the code that you developed in the exercises of lecture 8, but let's here use the built-in backslash that you get from the linear algebra module. We know the exact, so the exact x are the ones, so this is x here, and we make a table with norms. So you can actually define a matrix with the errors in there, or you can, if you do the calculation, you can also print the errors, preferably in scientific format with a small fraction, but to emphasize the exponent, the exponent. So if you look at the progression of the table of errors, then you will see that the errors will change. You could expect that if the matrices are getting larger, you get more round-off. So this is where the dimension n comes in. But actually, the crucial factor will be that k. You will see that the errors actually get larger, larger, and larger. So now it may still be okay. So you may still have 4 decimal places correct, but that's actually not simply good enough. So this is with the lufac without the pivoting. So this exercise is also an exercise to motivate the row pivoting. But does this in a way more systematic way rather than what we did with the first example, with the small epsilon. All right, then, so we have arrived at the second part in this lecture. So we will do the PLU factorization, where the P stands for the pivoting or the permutation matrix. So here is how the progression of the LU factorization works. It's a column-oriented algorithm. So we start with the first column, and we will interchange the column by taking actually the largest element. So you could look for, so the exercises, so the two examples, the two motivating examples, showed what went wrong if we had small numbers in them. So in a mathematical algorithm, you would only interchange rows when elements are exactly zero. Here actually, so because with dividing by zero you cannot do, but actually also dividing by very small numbers is very bad. Now, as we have seen with the first motivating example, dividing a very small number doesn't cause any harm. Or you could also say dividing by a very large number will not cause harm, will not actually lead to inaccurate results. So the punchline of the pivoting algorithm is that what we actually are looking for is we're not looking for smallest element. So you could also, a hybrid would be as soon as your element on the diagonal is less than 10 to the power minus 4, you look for a larger one. No, we will actually always look for the largest element in the current column, starting at the current row. So if you see on the picture on the progression of the algorithm, we actually have already reduced the upper right corner of the matrix. So the looking for the pivots actually goes to smaller and smaller columns. So the row reduction is the same. So the cost, the main, the expensive, the most expensive phase in this algorithm is still the reduction. So we still have that double loop sitting in there, and so this is so finding the large element is actually also a loop, but it is a loop that is a single loop. Here actually we still have the double loops in step 3. So yes, this algorithm is more complicated, but its cost is not causing a higher order. So the cost is actually still quadratic opposed to the cubic cost in the dimension of the reduction. All right. How do you do an LU factorization in Julia? So there will be, or there is a code posted at the course website, but the LU is already built in. So the LU returns 3 matrices: the lower triangular, the upper triangular, and the permutation matrix. So the permutation matrix is actually stored as a column very efficiently. So here to save space on the slide, I print it as a row vector. So you can see, first of all, how accurate this is. So this is here the full check on comparing the L times U with the original matrix permuted. So actually what we do is we have P times A equals L times U. So you have two products sitting in here. You have the product with the permutation matrix, and you have the product of L with U. Now we said that the product of the permutation matrix is actually a matrix multiplication. But you see here in the syntax of the Julia syntax here that the permutation can actually be executed very efficiently. It's just a row indexing, so it doesn't really involve any calculation. And the punchline, of course, is that the difference is of the order machine precision. So for a random 10 by 10 matrix, this is done very, very accurately. So this is the built-in LU factorization in Julia. So here is a little bit in greater detail what is these what the permutation matrices are doing. So a permutation matrix is represented by a vector in shorthand notation, but in general, a permutation as a matrix is a matrix where there is exactly 1, 1 on every row and in every column. And what you actually store are the columns of the first 0. So here we store the 4 because in the first non-zero, so the first one on row 1 occurs in column 4. And you see that this implies that actually the if you do the matrix vector multiplication, this means that the 4th element becomes first. So you can see that if you know the shorthand notation, that actually you can do this matrix vector multiplication. You can permute the elements in the vector, and just by indexing. So you take the first element in your new vector was the 4th element in the original vector. The second element is the 9th vector, was the 9th element. So you can read off how the indexing happened. So it's a simple scan through the vector to do the matrix vector multiplication. All right, here is the pseudocode notation for the LU factorization with pivoting. I will not show the entire Julia function, but it's only slightly longer than the pseudocode. So the looking for the pivot is here expressed still in mathematical notation. So we are in the current row J, and we look for the kth element starting at row I. The current row is actually the current column. We look for the largest element. And then if that index k is not the current column index, we do the swap with the tuple assignment. And then we have the reduction. So this algorithm is still very short because we do not really, well, actually it is short because it is an in-place algorithm. So it will change the matrix A. The upper triangular part will contain the row-reduced form of A, and the lower triangular part contains all the multipliers. In the post-Julia code, that's actually a functional implementation. Here we have an in-place notation. So there are 3 return elements. We have the lower triangular part of A, the upper triangular part of A for L and U, and then we also have the permutation matrix, which is returned as a vector. So here you see how this vector is changed with each permutation. All right, how do we swap rows in a matrix in Julia? Well, very simple. So we can do the tuple assignment. So there is no need for a temporary placeholder element. So This slide simply demonstrates the advantages of the tuple assignment. All right, then, let's now look at a numerical example. So this is an example that comes from the time of the scientific calculator. I'm still transitioning to the Jupyter time. I still have not done this, so this is a little bit my own homework. This should be reformatted in the cells of a Jupyter notebook. So I kept the example because it still shows it's a hybrid, so in a way it's a hand-by-hand calculation, but we are using real numbers formatted in scientific format. The accuracy of our formatting is 4 decimal places, so we count all the decimals that we see, also the ones before the dot. All right, here you see in this by hand calculation, we actually store the permutations as an extra column that we add. So initially the extra column is 1, 2, and 3. But observe here is that the largest number, and it may be a little bit deceptive because we actually should look at the exponent. So you see here the largest number occurs at the 3rd position in the 1st column. So in going from the matrix A above to the matrix A below, we have swapped the 1st row with the 3rd row. And that is expressed, the swap is done here. We record the swap by 3, 2, 1. So we should read the matrix as from bottom to top. All right, so let's now do the reduction. This is something that we also noticed in lecture 8. So it's a column-oriented algorithm, but we can already compute the multipliers, all the multipliers that we need that come from the 1st column. And that is also done here. So we are now reducing this part. So the 1st row is now okay, but we are going to reduce this part using the multipliers defined by here the numerator, and then we have the 2 denominators that are coming from the elements. So we have our multipliers, and the multipliers will be stored here. So the multipliers will be stored in the place of the 1st column. So you have to believe these calculations. You can compute them also by running essentially the we're going to see that example again with the Julia function that does the pivoting. All right, so we see now that actually we don't need to pivot. So here actually we do have to pivot, I'm sorry. I was looking still in the 1st column. So actually now we look at the 2nd column. So we have the reduction step, but now here we have the next step. And you can see that we are now knowing that we have to look first at the exponents. We now see that the 2nd number is again the largest number. And so we pivot. So that will lead to an interchanging of these 2 numbers here. So this should be a 1 and this should be a 2 if we write this properly here. All right, so here we are now close to the last step. So in the last step, we are doing one more row reduction. So we just copied the first, what was at the last matrix on the previous slide. So now with the interchanging. So we reduce, and then what is actually happening is that we store the multiplier. So the multiplier here is the evaluated coefficient here. Actually, it is without the sign. So I was a little bit too enthusiastic because there is a negative. All right, so these are the essential steps in the LU factorization with the row pivoting. Check is often to compute the determinant. So if you want to know whether this is correct, well, you compute the product of the diagonal elements, and then you compare with the determinant. So the product of these three diagonal elements should equal the determinant with a sign change. But here for this particular example, we changed twice. We changed the rows twice. So from your linear algebra course, you still may remember that if you interchange two rows, the sign of the determinant of the matrix flips. But here we've interchanged twice. So flipping the sign twice actually doesn't change the original sign. All right, then what is this example now? Well, we have the final output. So here the output are all the numbers, and then augmented with the information of the permutation. So we then write the permutation matrix in its full glory. So remember, the 3 here is the position of the 1 in the first row. So that's why we have here 0, 0, 1, because we have a 3 sitting here. Then we have a 1, and then we have the 2. So we copy the upper triangular elements and we copy the lower triangular elements. So if we have saved the original matrix, and we did, then actually we can verify that P times A will actually lead to L times U. Here are two exercises, and they work with the same matrix. So the first exercise is, or actually it's the exercise 3. You can solve this with SymPy. So if you are a bit, the numbers are small, but working with exact rational arithmetic often leads to expressions well. So doing this by hand could get tedious. Now, the difference with lecture 8, so we had a similar exercise to that in lecture 8, is actually that we will do row pivoting. So you can see the first element here, the first pivot that you will take will be 3. So you will, because 3 is the largest element in the first column. So the first step is actually the row interchange. So 3, 1, 2 will be your first row in the new matrix A. So, and you will have to work with 1/3. So the purpose of this exercise 3 is that you can go through the logic of the steps without having to be bothered with scientific notation of the numbers. Then you do again exercise, the same exercise, but now you do it with the partial pivoting, and you write all the floating point numbers in scientific format. If you still have a scientific calculator, then this is a good use of it. Otherwise, you could use the posted program with this lecture. That program will actually output all the intermediate matrices. So we can compare then the results with the results of exercise 2. So the main purpose of this exercise 4 is actually to see that working in exact rational arithmetic is actually overkill. If you're satisfied with the double precision of 16 decimal places, then actually the floating point arithmetic will have given you exactly the same correct answers as in exercise 3. All right. So now in the remaining 10 minutes of this lecture, I will say something about the new function to do the LU factorization. This is an educational program, and its main virtue is actually the verbose flag. So that will actually, in every step, write the matrix. So just like we did with the by hand calculations, aided with the scientific calculator, we will actually now see the progress of the matrix. And by hand, you get kind of tired of it already in dimension 3, but the computer doesn't get tired, so you can do higher and higher dimensions. Also, the stepwise, so the printing also gives you an idea of the total cost of this algorithm. You see, although this algorithm has a more complicated logic, the actual work is still in the reductions. So you can also see how this P is represented. Now I took the same matrix, and in Julia you can format the matrix so that you have you see just the amount of decimal places, so you just see this, the kind of amount of numerical information that you like. Here is a run with the program. You see also here, we know this now because we look at the exponent. So we have the largest exponent in the third row. We actually will have a swap. The program prints out the pivot row, and then it prints out the matrix before and after the update. You see that the third row now has become the first row, and we actually then see that the rest of the matrix has changed. So the first column of the new A has been replaced with the multipliers. And we're going to look now in the second column for the pivot. So there will be another pivoting happening. So it's still pivot row 3, but actually we will actually flip. So here you see the updates. And finally, the final matrix. All right, so this is a terminal output. If you run this within a Jupyter notebook, you do not copy the main program again. Actually, the main program is actually replaced simply by the function call. Perhaps I should have pointed that out. So you look at the example code that is in the documentation of the function, and that is actually what you copy in an execution cell. So if you would look at the posted program, you will see that it is interactive. So it actually starts asking about the whether you want a random input or whether you want the example input. So if you want to do a specific matrix. So here on this final slide, it actually shows the final result. So we have the matrix defined by the pivoting vector 3, 1, 2. We have the lower triangular matrix with ones on the diagonal, and then we have the upper triangular matrix. So we can still check this now. So in some sense, this is an advantage with the scientific calculators. Well, some scientific calculators will do a matrix multiplication. So but here it's actually a lot easier once we have extracted, or actually the L and the U will actually be returned to you, so you don't have to extract anything. So you can do the product of the lower with the upper, and we then look at the permuted input matrix. So for the permuted input matrix, we actually use the notation where we do an indexing with a vector. So we select the elements on the rows defined by the permutation vector, and we select all columns. So this is the permuted input matrix. Now we printed everything out with 4 decimal places, but you can see that the difference is actually machine precision. So this was a great calculation. So now let's do this a little bit more systematically. So we had our second exercise that was constructing matrices with very small diagonal elements. So here we do this exercise 2 again. So I give you some hints how to make the matrix R, and also actually somehow importantly, so in some sense this is the importance of this exercise. So if you want to solve then the system, you have to permute the vector B. So on the previous slide, I simply redrew again the permutation instruction on the matrix A. We must also permute the right-hand side vector B. So I just circled this here. Now, the results will be rather boring of this exercise. So the errors will actually all be of the machine precision. So there will be not much change. So you should actually do this exercise right after exercise 2. So the exercise 2, already large errors started to creep in as the K was also getting larger. All right, so the importance of the whole lecture now is actually that we have a numerically stable algorithm. I will define what is numerical stability. So I have arrived at the most important slide of this lecture, at least conceptually. So I suggested already with exercise 2 is that you would compute the condition number. So you can do that again with exercise 5. The matrices that we generated had small elements on their diagonal, but the condition number was still fine. So they were still random matrices. So if we do not do pivoting with the algorithm of lecture 8, then actually we had huge errors. And row reduction without pivoting is an example of a numerically unstable algorithm. Row reduction with pivoting, so the main topic essentially of this lecture, is numerically stable. And now we can define what we mean by a numerically stable algorithm. So if we have very small error on the input, then we also have very small errors on the output. So here the algorithm is defined as the evaluation of a function. So we have seen two functions. So the f is the lufac from lecture 8, or is the lufac of this lecture. So we have two different f's, where the input is the matrix A, and the output, and so the input is also the right hand side, and the output is the solution to the linear system. So this definition sounds very similar to the definition of condition number. And I want to end with this. So we define numerical stability ladder late in this course, only lecture 10, whereas already in lecture 4 I came up with conditioning. So conditioning is the main question if you look into a problem. Stability is the main question if you look into an algorithm. But the question of stability can only be answered, is only meaningful if you work on a well-conditioned problem. So you will also see huge accumulation of round off, or you will see very inaccurate results if we work with ill-conditioned matrices. So that was the conclusion of lecture 9. In lecture 9, we could fabricate matrices, and the backslash operator was giving us very, very inaccurate results. Here we also fabricate matrices, but the matrices are actually well conditioned, but they were fabricated in such a way that if you did not pivot it, then you obtained very inaccurate results. All right, so this is the grand conclusion of this lecture. In this course, we care about efficiency and accuracy. We care about numerically stable algorithms that we execute on well-conditioned inputs.